Hi, I'd like to finish up the example for data augmentation. And so here's a example. So the Gaussian mixture model. So remember the Gaussian mixture model, we have several groups, and then so this pi g is the proportion of the group, and this is the Gaussian model with the local group specific model, right? So in that group, we have a normal. Within that group, we have normal, but we have a multiple groups, basically. So then here we have pi is unknown. So pi is unknown parameter and mu is the unknown. Mu g is the unknown parameter. But let's assume that we know sigma square and g. And then goal is you want to make a Bayesian inference for setup, which is the pi part and mu part. So we already covered Gaussian mixture model can be explained by using a vector of latent variables. So let's use z. So z equal to 1, z1 equal so we have each component of z is just a binary, either 1 or 0. But the sum of the g should be 1 because each element belongs to one and only one group. Okay. So then this is basically pi g, right? Pi g, and this is normal mu g sigma square. So this mu g basically is a group specific parameter. And so because we have a parameter, two unknown parameters, basically pi g and mu g, so we want to impose a prior to build a Bayesian inference. So prior distribution for proportion. So previously in the proportion we use beta distribution, right? And now we have multiple groups. So it's not just a binary proportion. We have a multiple group. So then the multivariate extension of beta distribution is Dirichlet distribution. So this is a Dirichlet distribution density function, which can serve as a prior distribution for pi 1 to pi g. And then for the mean part, we just assume normal, right? So this is normal prior distribution, and these are the hyperparameters. So we won't worry about hyperparameter at this point. So then to apply the data augmentation, remember we have a parameter. So parameter is pi g basically and mu g. And then latent is g. So this is the latent variable. And this is a parameter. So then the model, so latent variable is just a random variable. So the model, the joint model is basically we have a data and z given parameter theta, and then parameter is actually we can write it pi and g, pi g and mu, right? And then we have a prior. So this is the likelihood part, and this is the prior part. So basically, this is the likelihood part. So joint likelihood of the derived. So joint likelihood derived from the joint density of the Ci and Yi. Okay, and then this is then the first two is a prior. So prior, the first component is the prior for pi. The second component is the prior for mu g, right? And then this likelihood is actually we can write it as a y given z and nz fz. So for fz part we have a, so what is the density of z? Just the density of z is a multinomial in some sense, right? You have a pi 1, c1, pi 2, c2, pi g, cg. So that is the density. So that corresponds to fg given parameter. And then what is the y given z? It's just normal, right? So if you know the group, then we know that y follows normal. So that is the proportional to exponential minus y minus mu g square. So combine these two, right? So multiply these two, you obtain this one. So that is the basically the likelihood part, and then we have prior part. So this is the joint distribution, and now we want to derive the full conditionals. So first one is, so remember we want to generate the three: z, m pi g, and mu g, right? So we actually have a zg, pi g, and mu g given y. And but that is not easy. So what we want to do is we want to generate y, pi g, and mu g first. So that is the first one. And second is pi g. So full conditional, right? Y and cg and mu g. And three, mu g given y and zg and pi g. So that gives, constitute the Gibbs sampling, which is the data augmentation algorithm that we want to apply to this mixture model. So the first one, the first conditional model, full conditional is about this one. So what is the conditional distribution of z equal to, right? Z, we already know that z is either 1 or 0. So then this is basically proportional to the marginal distribution times conditional data and z given ci equal to 1. So, oops, sorry. I think it's just this one. So this guy is a pi g, and this guy is a normal mu g and sigma square. So then we have this one. Okay. Second one, what is the marginal distribution? So, original one. Okay. So this we have prior, right? We have prior is just a Dirichlet. Prior is Dirichlet alpha 1 to alpha g. And then posterior, given x and y, no x, y and z, right? Given y and z and mu z. What really matters is only z, because basically the conditional distribution of f, y, and z given pi g and music matters. It is a matters. Oh, sorry. Okay, let me do it more closely. So this one, I mean the parameter. Okay. You have something like this, right? I mean, you have basically specification. Oops. What am I doing? So this is actual condition. So if you do that, okay, equal. So what we are interested in is a posterior, but we want to only consider pi, right? So that we have a music here. So basically here we have a prior of pi, which is a Dirichlet, right? Which is this one. And then this guy here. Okay. And now, so let's investigate what is this. So we have basically y given z equal g, right? I mean, for each g, and then depends on music. And then this guy is what? What is the, so given pi, z, we have a multinomial. So essentially pi c1, pi 1 c1, dot 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 pi g cg. So that is the, basically this is the joint density part, and this is the likelihood part. This is a prior part. And then the first term is essentially constant to pi. Okay, doesn't really depend on pi. So we, because we only care about the distribution for pi, so this is actually constant, and so this only matters. So you have a prior, which is Dirichlet, and then you have a individual, and then you have a summation, right? I mean, you have a, so likelihood is a product of the marginal density, so that here you just have a summation of the I. So that actually becomes a Dirichlet distribution, because if you so if you look at this, you have a pi 1 to pi g and alpha 1 to alpha g. So if you look at the coefficient, the power corresponding to pi component, you just have add two things, right? You have a -1 here. So then that becomes a Dirichlet distribution. Finally, same story here. So you are interested in posterior, okay. You are interested in posterior distribution of mu g given data y and z, which is g, and pi g, right? And then this one is actually you want to do something like this: cg, mu g, and pi g. And then you have what? You have a prior. Your prior is is normal. So your prior is mu g right, at given z. Okay. Yeah. It So this one is normal, mu 0 and sigma 0 square. So that is the prior, sorry, here, right? And so actually you have a, it's actually product. Prior is a product G of the each one, FG, UG. And so each one has the same, right? Okay. So then this guy, if you look at this guy is what? What is the marginal distribution of Y, conditional distribution Y given the group? That is actually normal. Normal, mu G and sigma G, sigma square, right? So that actually, and now you have a product. So that means you actually have a multiple of them. So that becomes a normal plus normal. That is straightforward. Another posterior is also normal, right? So here you have a, so this is kind of a multi-level model. So you have a here and here. This is not really good. Sorry, this is, well, this is a little bit not really accurate. So your prior is mu. Doesn't really depends on mu 0, right? So you have prior. Okay, so basically, mu G is a normal, mu 0 and sigma 0 square, and then here is more like this guy is more like Y bar G follows given mu G follows normal mu G and sigma square divided by ng. Okay, so you use, so we have a prior and posterior, I mean the likelihood, and then combine these two, you get the usual convex combination of the two to get this one. Okay, so that we covered this kind of normal, right? Obtaining posterior from normal distribution. We covered that already, so I'll just present. So okay, so that is the basically the completes the explanation of the example. So for the GMM, so I will just move on to chapter 4 in our next class. Thank you and have a good weekend.